All right, so we've been building up a fairly rigorous foundation of computability theory, and in particular, we had a lot to say about computable enumerability. And what I'd like to do now is I would like to kind of make a guided tour, a much less kind of rigorous and careful, but nonetheless somewhat rigorous guided tour of metamathematics on our way to the incompleteness theorem, using the foundation we built up of computability kind of as a base. It's my hope that I don't have to necessarily define or explain everything fully on our way to the incompleteness theorem because of that computability base. If you follow me all the way here, then you have a system by which you can kind of understand the things I'm about to tell you. So with that said, let's kind of start to finish this up. So, metamathematics, what is it? What we're trying to do with metamathematics is we're trying to formalize the process of doing mathematics into mathematics. Now that is obviously a potentially very confusing task, and many people trying to learn this stuff find themselves very confused because they have to really keep track carefully of what is the math that I'm doing and what is the math that I'm talking about. That's kind of the point of confusion. You really have to be clear on that as you go. And I think that it'll be easier for us to do that because of our computability background. I think that'll make this a lot easier. But that is the idea. What we want to do is we want to formalize the act of doing mathematics into mathematics. And then we want to talk about mathematics mathematically. So, in my view, the act of doing mathematics boils down to a few components. So first of all, we have a language that we speak in. We actually have multiple languages. I'll talk about why that is. But for the moment, let's just say we have a language of mathematics. And what I mean by language is not the language I say out loud, but more importantly, the language that I write down on paper. We have a collection of symbols. We have an alphabet. We write Greek letters. We write digits. We write all sorts of things. And we also have, out of that, we can form valid sequences of letters. We can kind of form words, right? And so what we have essentially is like a rigorous grammar, a rigid and precise grammatical structure that kind of dictates the way that we can put these symbols together and express mathematics on paper. So I can put the letters together, and sometimes it'll mean something, sometimes it'll have something to say, and sometimes it won't. So that's one component, is the language that we speak in. The second component is, and I'm not going in order of what I wrote down here, is that obviously what do we want to study in mathematics? Well, we want to study objects. And what I mean by objects I mean kind of abstract theoretical objects. Now, I'm a materialist, so what I just said does not sit well with me. But nonetheless, and this is an important point, we're going to approach this stuff as idealists. We're going to approach it in the naive way that a mathematician naturally would, because this is the thing about mathematics, is that if you're doing mathematics, you have to talk about things that don't exist in reality as if they exist in some sense. And it's very tempting at that point to believe that they exist in some kind of higher plane or something, right? Even though they don't. We're lying to ourselves. There's a degree to which we are lying to ourselves just to do math, maybe. That'll be a whole discussion to have at the end. What I want to do with these videos is I want to just be a Platonist. I think I want to take the easy route and just approach this like a naive ancient Greek philosopher. We have these objects, these theoretical things, numbers, graphs that we want to talk about. And more importantly, we want to discover truth about these things. So I have this thing, it exists, called the natural numbers. What's true about it? What statements about it are true? What statements about it are false? Furthermore, we're going to have specific languages for the type of object we're going to study. So, for the natural numbers, we have certain things that we talk about, like addition and multiplication. With set theory, we have, certain symbols for like one set being in the other. We have specific languages for specific objects. So I wanted to make that clear. That's what I meant when I said we have multiple languages as mathematicians. Of course, there's kind of a base language at the bottom of like logical symbols that kind of apply to all fields of math. But we also have specific languages depending on the object that we're trying to study. And so the main task, once we have those two things in mind, a language to speak about an object and an object that we intend to discover truth about, the next thing we have to address is how do we discover truth about these objects? And so the way that mathematicians do that, the way that we found ourselves doing that, because remember, we started doing this, metamathematics, quite late into mathematics as a developing field. We observed ourselves behaving in a certain way. And so what we're doing is we're formalizing that observation. And the observation is that the way that we discover truth about objects is that we assume some basic facts about the object that everybody can agree on, called axioms. And then we have a formal proof system that most people hopefully can agree on, from those axioms and from basic logical axioms that are also kind of axioms but on a more basic level, we can form finite sequences of grammatically correct words made out of this language. We can form a set of statements, one after the other, that constitute what we call a proof. And the last line of a proof is, hopefully, the idea is that we come up with a proof system, right? And so the idea is that we have an object we want to study. We come up with some basic assumptions to make about that object called axioms, and then we come up with a system for formally proving things from those axioms. And then we say that we have discovered truth about the object because anything for which, assuming that the proof system is valid, that will mean that I've discovered new truth about anything such that those axioms are true, and that object is hopefully one of them, assuming that those axioms were actually true for it. So that's how mathematicians pursue truth about theoretical objects. So we sort of have four things that we need to talk about. We need to talk about the language of mathematics, the system of formal proofs, the objects of study, and the axioms themselves. And so to wrap up this introduction to the rest of these videos, I want to talk a little bit, preview a little bit, the way in which computability, or maybe one of the ways in which computability is going to repeatedly present itself to us as we go through this stuff. I'm not going to promise this is the only way, but it is a way that it presents itself enough times that I wanted to say it now. It pertains to a generalization that we're going to kind of observe as we go on. We've been talking about computability, the idea of trying to solve a problem on paper. But what we've ended up with are these finitely describable machines that in some sense correspond to infinite sets. And so we're going to be repeatedly faced with this question of what kinds of infinite sets can be described finitely? What does it mean for a set to be finitely describable? And the answer, we're going to see that this is the answer repeatedly, is that a set is finitely describable if and only if it's computably enumerable. And we're going to see that through repeated application of the Church-Turing thesis. And we're going to begin that discussion with a discussion of languages and formal grammars. So that's what we'll do in the next video.